Hello students, title of today's lecture is 4 probe technique for resistivity measurement. So it is a special technique which is used to measure the resistivity in case of semiconductor materials and thin films. So first let's discuss what is resistivity. You are already familiar with this term. Resistivity is actually the electrical resistance of a conductor of unit cross-sectional area and unit length. So suppose we have a conductor of the dimensions shown here in the figure. If A is the cross-sectional area and L is length of this conductor, then you know the resistivity is given by this expression. So that is R into cross-sectional area divided by length. So if cross-sectional area is unity, length is also unit, then resistivity is the resistance offered by conductor of the given dimensions that is unit cross-sectional area and unit length. Now the measurement of resistivity normally is done with these units. Typically it is ohm meter, or sometime it is also mentioned as ohm centimeter. Now we have to move forward. We have to learn how to measure the resistivity. So if you want to find out resistivity, the best way is first to find out the resistance of the given conductor. For finding the resistance, so the simplest technique which comes to our mind is to measure the amount of voltage appeared across this given resistance part when a known amount of current is passing through this. So we can make this kind of arrangement. We can allow I amount of current to pass through this. So when this I amount of current is passing through this, at that time some voltage drop will occur across this resistance. We can measure that voltage, how much voltage is appearing across this. So now we know the voltage drop across it, and we know I. So from this ratio of V and I, we can find out how much is the resistance. And once we know the resistance, then from this equation we can put the value R here. We should also know the actual dimensions of this conductor. So its cross-sectional area and its length. So that way it is possible to find out the resistivity. So normally the equation of resistivity in case of n-type semiconductors is given by this expression. So you can see here resistivity is inverse of this term. So it is inversely proportional to n, the density of electrons. So higher the density, lower will be the resistivity, because higher density means higher conductivity. Of course resistivity will be lower. It is also inversely proportional to the mobility of the electrons. If it is a p-type semiconductor, then n is replaced by p, and this term the mobility is considered in case of the considered value of mobility is for p-type carriers. And if a semiconductor have both type of carriers, that is n-type as well as p-type, then the equation of resistivity is given by this. So both these terms are combined here, right? Now this two probe method which is discussed here, this is a two probe method. So one probe is connected to one side of this device, and second probe is connected to this second side. So this is known as two probe method. So now we have to see what are the problems associated with this kind of simple arrangement for measuring the resistance. We will consider two different cases. First we will talk about the bulk samples, and then we will talk about the thin film samples. So let's see in case of bulk samples what happens. Now suppose we are making this kind of arrangement. We are allowing I amount of current to pass through this resistance, and we are measuring V voltage which is appearing across this conductor. And from this we can find out the resistance, total resistance of the device. But we have to remember that this resistance which we are measuring using this technique, it contains not only the resistance of this resistor, but it contains some other components also, other resistive component also, so which are represented here in this circuit. Suppose this I amount of current we are allowing to pass through this circuit. So suppose this current is going like this is I amount of current. Now the voltage which we are measuring with the help of this voltmeter, that voltage is, of course, that is considering the resistance of device under test. This is device under test, but it also includes some other resistance like RW. This is wire resistance, the wire resistance on this side, and here this contact. So where the probes are touching this part, so this contact resistance is also coming into picture. So it is actually here. So the resistor or this device under test is connected to the external wires. So that is a metal semiconductor contact, and that contact also offers some resistance. So the voltage which we are measuring, that voltage is not across, not just across the resistance of device under test, but it also appears across the contact resistance and also across the this wire resistance. So the total equation of voltage which is measured by this voltmeter, that is given by, like, I is the current which is passing through this into wire resistance, and it is 2 times because 2 wire resistance components are shown here, plus then this contact resistance is also there, RC. So I into RC, this voltage drop appear across one side of contact, but there are 2 such contacts, so it will be like this. And then of course this R device under test resistance offered by this into I. So the voltage which is being measured by this voltmeter, that have this component which include the voltage appeared across the wires, the voltage which appears across the contacts, and the voltage which appears across the device under test. We are basically interested in this, and but the voltage which is being measured here, that have these unwanted components also. Now if you want to find out this total resistance of the entire system, that total resistance will be given by this expression. So V divided by I is common in all these. So V divided by I, that is RT, total resistance. That includes 2 times the wire resistance, 2 times the contact resistance, and of course the resistance of device under test. So these are unwanted components which will create problem. Because what we are assuming, that the voltage which is being measured with the help of this multimeter or voltmeter, that voltage is the voltage which is appearing across the device under test. So if we are using this RT in the calculation of resistivity, we will get definitely a wrong value of resistivity, right? So basically these 2 contact methods, so I told you it is 2 contact method. So it have basically 2 point contact, and each contact serve as a current and as a voltage probe. So for example, this same contact that is serving as the current probe, means current is supplied to this device under test through this probe, and the same contact is being used to measure the voltage. You can see here the voltmeter is connected here. The voltage measurement is also being done by the same pair of contacts, and the same pair of contacts are used to insert the current into the system. So this kind of system, this kind of measurement appears very simple. Just we have to measure the voltage which is appearing across this device when I amount of current is passing through this, and the total resistance, which is the ratio of V and I, that can help us to find out the resistivity. But since this total resistance includes other components also, so whatever value of resistivity we are calculating, we are going to get a wrong value, right? So it is mentioned here, you can see this method appears to be easier, but the interpretation of the measured data is difficult due to various resistance inclusions, because other components they are also included here. So that's why we are expected to get wrong results, because you know the rho is given by R A by L. So if this R is total resistance RT, so this RT is not the resistance of the device under test, but this RT have other components also. So that's why this rho will have error. This is the main limitation of a two probe system. So whatever we have discussed so far in this slide, that is for a bulk sample. Most of the time in the semiconductor industry, we have to work with the semiconductor surface and thin films. So if we are using this method to find out the resistivity of a semiconductor surface or of a thin film, in that case we have to make this kind of arrangement. So the probe, these two probes, they are touching the surface of semiconductor, and this part is the resistance offered by the semiconductor. So there is a contact here, and this is probe, and the I amount of current is going here inside, and now it is coming out from this side, right? And V voltage is measured between these two probes. The same probes, the same pair of probes is used for supplying current into the system and also for measurement of voltage across it. Now what is coming here? So as in case of bulk sample, this RW was coming. So similarly here RP, this is probe resistance, resistance offered by the probe, that is coming here. And here at the contact also, so this RC component is coming, that is contact resistance. So this contact is offering some resistance, that is contact resistance. This probe is offering some resistance, that is RP. And one more term is coming here, that is RSP, which is known as spreading resistance. It is because of current spreading. So if we have this kind of flat surface or thin film, then this probe is a narrow dimension as compared to the area of this surface. So when the current enter into the semiconductor surface, it starts spreading like this. It spreads like this. So this spreading phenomena adds more complexity, and these complexities are represented by the presence of the spreading resistance. So in this case, total resistance, which is a ratio of V by I, that total resistance have of course 2 into Rp. So Rp is probe resistance, it is similar to the wire resistance. Then 2 time contact resistance, just like here, which was present in case of bulk samples also. There is one more term here, 2 times spreading resistance. 2 probes are there and both have this kind of spreading components. So that RSP here and RSP here. At these two contacts, the RSP will come into play. So it is 2 into RSP that is coming, plus RS. RS is the main resistance in which we are interested, and that is the resistance which is offered by the semiconductor. So we are interested actually in this, and these are some unwanted components. So whatever resistance we are measuring here using this kind of arrangement, a voltage measurement arrangement, so the total resistance which we are getting, that contains some unwanted, some parasitic effects. What we want that the total resistance should include only the resistance of interest, that is RS, but it is not happening. So if we are going to do measurements like this, these unwanted components, they will stay here, and they are problem creator, because they are making problem, they are problem, because they are giving us a value of R which is different from the value of semiconductor resistance. So if we are going to use this RT here in this equation, so of course we are going to get problems here. So we have to make some modifications into the measurement system so that these 3 components disappear from this equation, or they become irrelevant. So for that we have to develop a 4 probe method, which we are going to discuss into the next slide. I hope that now the limitations of 2 probe methods are clear to you. So we have discussed this 2 probe method with its limitations in case of bulk samples and also in case of semiconductor surface or thin films. Now let's discuss what is this 4 probe measurements. Now first let's see in case of bulk samples. So the arrangement look like this. There are 4 probes here, means 4 contact. One contact here you see, that is for current. So I amount of current is going into this device under test through this path, and then it is coming out from this path. And there are 2 other probes also, one this and one this. So these are part of a second loop, and this loop is only for the voltage measurement. Now let's see what kind of benefit this kind of arrangement is going to give us. Uh, so you have seen in the earlier slide that if we use a 2 probe setup, the total resistance is given by this total resistance, which is measured by voltmeter, that includes wire resistance and contact resistance, and of course the resistance of the device under test. And the equation of voltage was like this: 2 into I R W plus 2 into I into RC plus I into R DUT. It was like this. Now here in this new arrangement, if you see here, the inner loop which is used for the voltage measurement, we have to apply this KVL here. Now this voltage measurement, that is done with the help of 2 additional contacts. You can see here, these are 2 additional contacts. The current loop is same as before, only modification is that this new path is used for the voltage measurement. Now input impedance of voltmeter is very high. It is about 10 to power 12 ohms, or maybe higher than this. So the amount of current which is passing through the voltage loop, that is negligible. So the amount of current which is passing through here, that I is almost 0, right? And but this I which is there in the current loop, that is not 0, that is supplied by the external current source. Now because of this reason, if you look at this voltage loop, now since this I is negligible, so voltage contributed by this component is almost 0. Voltage contributed by this component is also almost 0, because we are taking I which is passing through this part. But here the voltage across this device under test, that have 2 currents, both currents. One is this I which is in the current in the voltage loop, and there is one more current actually here. I should include here this component actually will not be like this. This component will be I plus I1, that into R DUT, device under test. Oh my god, yeah, this is I1, and I1 is, suppose, the current which is passing through the outer current loop. So now as I told you, the impedance of this voltmeter is almost infinity, so negligible amount of current is passing through this. So this I is 0, so this part will be 0, this part will become 0, this I is 0 here, but the voltage across this device under test, that will have I1 into RD out. So the voltage here, that will be I1 into RD device under test. Now from here we can find out R, and this R will be V divided by I1, and that is actually your resistance of device under test. So that way the total resistance which you are measuring here in this kind of arrangement, that have only one dominating component, which is RDUT, right? And other components like wire resistance and contact resistance and the spreading resistance, those components are no more present here. So whatever total resistance we are measuring with the help of this 4 probe method, that is the actual resistance in which we are interested. And now if we are going to apply this RT value here in this equation, what we are going to get, we are going to get more accurate value of rho, because this RT have less error, you can say, less parasitic components present into it, or negligible parasitic component into it. It truly represent the resistance of the device under test. So you can see here it is mentioned the voltage drop across RW and RC are negligibly small and can be neglected, and the measured value is essentially the voltage drop across the device under test. So this is the main advantage of 4 probe technique. Now suppose we are going to use this 4 probe technique for measuring the semiconductor surface or thin film resistance or resistivity. The arrangement look like this. So the outer two probes, they are for the current, and the inner probes, probe number 2 and probe number 3, they are for the voltage measurement, right? And now the KVL will be applied in case of this inner loop, and since voltage resistance is very high, so the voltage drop across the wire resistance, wire 2 and 3, so that voltage drop is negligible. Voltage drop across these two contacts, that also is negligible. Voltage drop across spreading resistance is also negligible. So whatever voltage drop is coming into picture, that voltage drop is because of this semiconductor resistance. The reason is that through the semiconductor, another current I, which is here in the outer probes, that I1, that is passing through this. So here resistance, the voltage across this is I1 into Rs, right? So this V which is being measured, that is actually I1 into Rs. This is the true representation of the same 4 probe arrangement. The contacts are indicated with the help of resistive components. The wires are also the resistance offered by wires is also represented by the resistance values here. These are contact resistance, and these components are the semiconductor resistances, which is coming between the probes. So between the voltage probe, this RS2 component that is coming into picture. So whatever voltage is being measured by this voltmeter, that is the voltage which appear across this RS2. The voltage appearing across other component like RC2 and RC3, that is negligible. Voltage drop across RW2 and RW3, that also is negligible. So whatever voltage we are measuring here, that is true representation of voltage drop across the semiconductor part only, and that way we can use that value of resistance to find out the resistivity. So the 4 probe method, as indicated in figure, has 4 equally spaced inline probes with probe tip diameter small as compared to probe spacing S. So the tip of the probes, remember, the tips should be very small as compared to spacing between the probes, and here you can see this arrangement. The equally spaced probes are there, means the gap between first and second probe, gap between second and third probe, and gap between third and fourth probe, they are same S, and they are in a single line, right? So that's why they are known as collinear probes sometimes. Now here you can see a practical example of 4 probe measurement which is being done on the thin films. You can see here in this diagram, in this photograph, there are some lines, bright lines. These bright lines actually metal interconnecting lines. So you know, when we fabricate a electronic circuit, in order to interconnect the devices, we make metal lines. So these metal lines are represented here in this photograph, and what we are doing, we are trying to measure the resistivity, or first we have to measure the resistance of these metal lines. You can see here 2 probes are placed here at a distance of 292 micrometer, and width of this line is 54.78 micrometer. So you can imagine how small it is. The diameter of our hair is about 100 micrometer, so it is less than the thickness of hair. So it is very difficult to view it with the normal microscope. We normally use electron microscopes to get these kind of pictures. So this picture is obtained by scanning electron microscope, not the optical microscope. So but here you can see 2 probes are being used here, and in the second figure you can see here again interconnecting lines are there. There is a pad, metal pad, again the other side also some metal pad may be there, it is not shown in the figure, and these pads, they are connected through the lines. You can see here the lines are going like this, right? So you can see in this in case of this line, this particular pad, the line which is going here, So there is one probe here and one probe here. These outer probes, outer two probes, they are current probe. So the current is inserting here and current is coming out from here. It is going like this. And between the outer two current probes, there are two voltage probes. So this is one voltage probe and this is second voltage probe. So they are touching the same line. So that way we can measure the voltage which is appearing across this part of the metal line, and this voltage will give you the actual value of resistance which is coming between the two voltage probes. And from this resistance value we can find out the resistivity of this deposited metal, because the dimensions of this line we know its cross sectional area, we know its length. So once we know this resistance, we put this resistance here and put these values A and L here, and that way we can find out the that this topic is clear to you. So if you have any doubt, you can discuss with me in the interaction session.